Hello, welcome to lesson 6 of topic 4. In this lesson we're going to learn about critical angle, total internal reflection, and optical fibers as an application. Okay, first I'm going to give you a little activity you can try at home yourself. Fill up a transparent container with some water and then take any object which will sink in the water. In my case, I'm going to take my little oscillating man, put it on the side, and lower your head and look up from underneath the surface. Can you see the reflection? Here's another object I already placed. Again, my decorative beads, and there they are. The surface acts like a mirror. Here's another example. As you watch this, other than the fact that these kids are really having fun, look at the water. How is the water green? So let's begin. When light goes from a more dense to a less dense medium, where it's going to be in a more free medium, in other words, where it gets faster, its direction moves away from the normal line. So in this case, if light is going from the dense medium to the less dense medium, then that's the normal line. This is the angle of incidence. And you can see that the angle of refraction is larger than the angle of incidence. This is because it is faster in the second medium than it is in the first medium. We've learned this in the previous lesson when we learned about refraction. Now we're going to discuss an application. I want you to think about what happens to the angle of refraction if I increase the angle of incidence. As I increase the angle of incidence, the angle of refraction will also get bigger. But in this case, the angle of refraction is larger than the angle of incidence. And since it is larger than the angle of incidence, at some point it can actually reach 90 degrees. What will happen then? Let's see. So here's a container I can put some water in. We have light passing from water to air. Right now the angle of incidence started as 0. And you can see this is the angle of incidence right here, and that's the angle of refraction right here. And at that point right there, you see light no longer gets out. Similar case from glass to air. And again, we see that at that moment exactly, light cannot get out of the boundary over here, but instead we see it reflecting back inside. So, when refracting into a medium where light moves faster, the critical angle, C, is the name given to the angle of incidence, which causes the angle of refraction to be 90 degrees. Here's an explanation. Let's talk about how we can calculate the critical angle. Before we do that, what do you think the critical angle depends on? Do you think it would be the same for every medium? For example, the critical angle for glass and the critical angle for water, do you think it would be the same? Let's see. At the beginning of the previous lesson, do you remember I put a coin under a glass beaker and filled it up with water, and from a certain angle we stopped seeing the coin. So instead of the coin, let's put a little fish under water. We are looking from above, trying to see the fish. Well, if we're looking straight from above, I can see the fish. This ray, since it's going out to a medium where it can move faster, light is going to deflect away from the normal. So instead of going straight, it might be doing that. Let's take another ray, which makes a bigger angle of incidence. This time, this angle of incidence is bigger than the one before, so the angle of refraction will also get bigger. Let's try even one more. This one can still leave into the next medium. There's going to be some point where the angle of incidence is going to be so big that the angle of refraction is equal to 90. Using Snell's law, let's say air is our first medium and water is our second medium. We learned that N2 over N1 equals sine of angle in medium 1 over sine of angle in medium 2. Since air is our medium 1, N1 is equal to 1, and N2 is the index of refraction of water. Sine of the angle in medium 1, the angle in medium 1 is 90 degrees. The angle in medium 2 is critical angle. We know sine 90 is 1, so I end up with that, which relates the critical angle to the index of refraction of the medium it's trying to get out from. Here's a calculated example for you. Index of refraction of water is given as 4 over 3. Critical angle for water would be inverse sine of 1 over n, rearranging the formula. So when you substitute 1 over n as 3 over 4, the critical angle is calculated to be 48.6 degrees. Now calculate the critical angle for diamond, given that its index of refraction is 2.417. If your answer is 24.4 degrees, you're right. That actually means it's much harder for light to get out of diamond, because any angle larger than 24.4 incident angle will not be able to leave into air. This formula is given in the data booklet. However, it's not given under topic 4 formulas. It is given in subtopic C3 as labeled as fiber optics. Even if you're not studying option C, this section should help you when you need the formula for the critical angle. All right, talking about total internal reflection, when the angle of incidence is equal to the critical angle, the angle of refraction is 90 degrees. So critical angle is the name of the angle of incidence, which causes the angle of refraction to be 90 degrees. That means it's the limit of light not being able to get out to the free medium. When the angle of incidence is larger than the critical angle, the wave is reflected back within the medium, which we call total internal reflection, following the laws of reflection. That turtle is an example, and the two examples we saw at the beginning of this lesson are also examples of total internal reflection. Optic fibers are what we use for communication in today's modern world. It's a cable made of thin, clear glass or plastic. Once light enters the cable, it's totally internally reflected until it reaches the far end. So, as the last demo of the day, this is a picture of an ornament, a decorative element that you might find in places like home center. Normal people would buy this to decorate their homes. When a physics teacher sees this, she buys it to break it apart and use it as lab equipment, like this. So these are what the fibers look like, and here is what I do with it. I put the base on a flashlight and look what happens. In each fiber, can you see the light getting out only at the tip? So until it reaches the other end, When light enters each fiber from the bottom, it only reflects inside several times until it reaches the opposite end, which is why that pretty sight can be seen. That's it for this lesson. I would like you to look at two questions for homework. One is May 2018, Time Zone 2, Standard Level Paper 2, Question 3, Part B. As you solve this question, please be careful. This is a sound wave. And the next question I'd like you to look at is November 17, Standard Level Paper 2, Question 4, Part 1. Thank you.